G'day. A friend of mine asked me to make up a little jig for him which involved cutting a lot of angles, and so I started thinking, well, that's an interesting topic in itself, is cutting angles on the mill, because if you think about a mill, it'll cut orthogonally quite happily, but when you start talking about going off on angles, then you start doing some interesting things. But I got a bit wrapped up in that, and so this particular video is more about measuring angles, and then there'll be another one about actually applying that to the mill. So this is, okay, how do we know what an angle is, and where does that come from, and all that sort of thing. First of all, how do we know what an angle is? Well, this thing is called a cylindrical square. It's called that because the base and the axis of it are perpendicular to a high degree. This one here lives in a little wooden box, and it rarely gets brought out. And the reason for this is basically a primary standard in this workshop. And what you do is, once you know what this is doing, you can then come along with all your other squares and you can put those up against there and say, is there daylight between there and there? Get some feeler gauges out if you need to, and then you can say, well, if this is perfectly square, this is square to within however many degrees. Okay? But how do you check this? Fortunately, it's relatively straightforward. What you do is you get a micrometer and you measure it top and bottom. From that you can say this shaft is parallel. Then you come along with an indicator stand like this. Now, you've probably seen these before. A number of YouTube machinists have got a device on there like this. What that's doing is providing you with a constant point to measure against. Provided this is the radius here is greater than the radius of the swing here, you're okay. But what you're going to do here is you're going to come along and you'll sweep that across. To do it this way, I think, so it can be seen. You'll sweep that across, right, until you get to, I guess, a maximum deflection, and that's 5/10 under the thing. Now, if I come 90 degrees to that and do the same thing, that's also reading about 5/10. Okay? Because that diameter and that diameter are the same, and the deflection from a known point down here to here is the same, this is actually perpendicular. Now, these things are ground, and if you look very carefully at this one, you can see the grind marks on them, but there's no reason that you couldn't play with your lathe and turn that up. If you wanted something, if all you had in your workshop was something like that, then you could use that, or you could make something up on your lathe to actually check that. And your lathe should turn that either concave or flat, but as you can see at the top here, there's just this little recess, which means that even if it is slightly convex because of that recess, it's going to sit on that rim there. Okay. Once you've determined that square, you can then go comparing everything else. So you can compare this. This is a rather second-hand granite square that I have, which I use with the surface plate here. And once again, that's square. That's good. I like that. Okay. If someone's asking or wants to know why granite, the reason is that if you have cast iron and it chips, or you drop something on it and it puts a ding in there, it'll also push up material outside. Whereas the granite, that it'll chip, it'll spall, and so it stays flat. Okay, that's pretty much the reason people like granite. So something like that ding in the corner there doesn't matter. Okay. That'll still be flat going up to there and flat to there and so on for a given value of flat. 90 degrees is a nice angle, but what do you do next? Well, if you're trying to get an angle which is not 90 degrees, you can use one of these, which is a sine bar. I've got two here, they're both imperial. I say that because the distance between the pins there is an imperial number. Okay, this one's a handy one because it's magnetic, whereas this one is just a plain bar. This is a 5-inch bar, that's a 2-inch bar. This relies on trig, and so to get a particular angle, you have to put gauge blocks underneath the back cylinder, and that will give you that angle. To get a say a 45-degree angle on this sine bar, that's actually 2.5 inches between centres. I think I said 2 before. With 2.5 as the hypotenuse, the sine of 45 degrees is 1.76 inches. I've made up a stack of gauge blocks to give me that number. Put them in there, and that should be 45 degrees. If I get out a protractor, that looks mighty close. How could I check that? Well, there's a 45-degree angle block. Now, some people have sets of these, and they stack them up a bit like slip gauges here to get any angle they want. I don't need that, so I haven't got anything like that. I tend to use the sine bar for precise angles. But if I put that on there, and I ran a dial indicator across the top there, that would tell me how close this block is to 45. Or if I knew this block was good, how close the sine bar was to 45. So it's really a matter of checking these things against each other. And if I wanted to, I guess I could, if I checked this on this bar and then I set up a stack and checked it on this bar, and I came with the same reading, I could conclude that, well, you know, this could be good. And then if I got that and put it on the sine on this sine bar and put that up at the 45-degree angle and measured that, I could check them. So by having 3 of something, you can actually check against each other. A moment ago I waved this thing in front of the camera. This is a Mitutoyo protractor, and this will read to minutes of degrees. So a degree is divided into 60 minutes, and a minute is divided into 60 seconds. And this is quite good. The only problem I have with this one is that because it's got a lens there to magnify, sometimes that catches the light and I can't see it. But that's another way of getting precise angles in your workshop. Okay, so if I did this, .45 degrees, put that in there, and that looks like that's pretty close. So that is probably pretty accurate. I think that when I bought it, this is an Amazon purchase, so when I bought it, it claimed to be within 20 minutes of the right angle. So while on the subject of angles, I should probably talk about a non-angle, flatness. This is a surface plate. It's made out of granite, and it's flat to within, well, offhand I wouldn't know, but it's flat to within very, very flat. The biggest problem with flatness is actually measuring the deviation, because if I put a dial gauge across here using this device, which is a homemade repeater meter, and that was graduated in, say, 0.1 of a millimetre, I wouldn't see the needle move. This one is actually graduated in microns, and as you can see, as I drag it across the surface there, I get very little variation. Okay. The basis is a heavy weight supported on 3 points with a 4th point here and a hinge, and that's a bit of spring steel as the hinge, and that as that goes across, that will show the deviation between this bit and this bit. Another way to measure flatness on these things is suspend a straight edge across the top and then run an indicator like this upside down on a little carriage, and if the straight edge is actually straight, flat, it will tell you what the deviation of the surface is. These days laser equipment is available, so you can do all sorts of funny things with lasers. Another possibility is one of these. This is a level. It's a reasonably precise one, 0.04 millimeters per meter, which means if you had this on something a meter long and lifted up 0.04 of a millimeter, you'd see the bubble move. And what you'd traditionally do is divide a surface plate up into a grid, and this is obviously for a much larger surface plate, and then you put this across the squares on the grid, and you notice what the level is, and by that you can work out, well, is it a constant slope or has it got a dip in it? And the dip of course means it's not as flat as if it was a constant slope. There are a couple of ways of measuring flatness. The problem with flatness, I guess, is really the precision you want. There's always an extra decimal point that you can measure to, and as I said, with laser interferometry you can get down to some incredible sorts of things, but then again, I put my hand on there, the heat from my hand warms up the granite a little bit, and that'll make the surface move. And how do we generate a flat surface in the first place? Well, classically it's done with three surfaces. And it works like this. If you put A and B together and scrape those until they're flat, scrape those until they match, and then you take B and put that with C and scrape those two till they match, and then you take C and you scrape that with A until they match. You repeat that cycle, just taking off the high spots, and eventually you get down to something where all three of them are flat surfaces. And now how far you want to take that is up to you. When you start getting down towards the micron level, one of my favourite stories about Mitutoyo is that the senior executive came to a laboratory where they were scraping surface plates, and he pointed out to them that they'd scrape and then they had to let it sit for half an hour for the thermal effects of the scraping to bring the surface down before they could actually measure that accurately. So even when you're just putting it on there, slight rub, it can affect it. Thanks for watching, and I hope that explains a bit of the whys behind angles and flatness and all those other fun things. Thanks to those who've inspired me, and we'll see you with the next one.